Yeah, let me echo what the previous speaker said and thank the organizers, Gediminas, and the whole team for a really very interesting, very smooth running meeting where many of us see old friends and make new ones. It's been fantastic, and we've been hearing fantastic talks, and I'm definitely learning a lot about vanilla BECs and whatever other flavors of BECs, cold gases, warm gases, ions, etc. exist. My talk will probably feel a little different as I'm more talking about sort of real world applications. I'll try to not only do that, but give you sort of a bit of a few examples of different ways atoms in my world can be used as probes to understand a little bit of physics, but then also things that are not in physics but elsewhere. So I should also mention I'm not only at the University of Sussex. In fact, last summer I moved from there. Mainly, I still maintain a presence there, but I moved to Germany's National Metrology Lab, PTB, in Berlin, where I'm now at the Department for Biosignals. So that already tells you it's not only about synthetic quantum systems in themselves, but perhaps use very simple ones to do something in another area of physics. So just to give a sense, so University of Sussex is here in the south of England, nice rolling hills near the beach. PTB, where we measure the lowest possible magnetic field measurement, we do the lowest possible magnetic field measurements that exist. Maybe not the best environment, but it's a historic site in the center of Berlin. So why would you be in the center of an urban environment? Well, the advantage is, of course, you can collaborate with the people who might want to use the type of systems that we want to use outside physics. And that's where we are. So it's kind of double the distance between that. I commute a lot between to come here. Not very far, but very nice to be here. So our atomic gases, yeah, we can have them as quantum gases, and we can trap them in our sort of specialty is to trap them in complex geometries on microscale, sometimes smaller nanoscale at low temperatures, tunable geometries, sort of individual rather than lattice geometries, individual traps with different shapes. But the other containers look very simple, but we're now making them sort of towards industrial scale, wafer scale, have little cells of silicon with 2 glass walls. This is the size of a pound or euro coin. And there's some atomic gas alkalis. The same atoms actually that are ultra cold here are warm in here, and they are at a few hundred kelvins in the thermal state, simpler to use, of course, in practical applications and more of them. So when we want to use atomic gases as probes, we can have it simple, like I just said, and then we're more ready to actually do real-world technology with it. So that's why this axis goes like this. If we increase the complexity of the system, and what I've been hearing here is, of course, going far beyond the things we do, and it's ever increasing, and ever increasing also our understanding of fundamental quantum physics phenomena in many body systems. And those could also become future metrology tools. And what I will try to do is give you sort of a few examples on that kind of scale. There are some basic tools in cold atoms that we've been developing over the years, as have many of the other labs. Sometimes people don't talk very much about all the details that need to happen, but it's actually quite a lot. So we've built, this is a meter stick with centimeter scale. So we've been building things on micro scale chips, but also printed circuit boards that go to millimeter, centimeter scale, and more recently 3D printed metals that you can now print your whole vacuum container. This is roughly this big of an assembly in shapes that you couldn't manufacture otherwise. And actually we can have cold atoms with those structures and integrate them with other structures, have water cooling inside vacuum chambers, etc., to also generate large magnetic fields to make Bose condensates in sort of simpler, smaller setups, which of course is important for on the journey towards more practical applications. We've also, this is mainly a result of the began in the lockdown phase where we weren't allowed to go to our lab, so we had to automate everything. And automizing everything is not only running the experiment, but is also reacting to uncontrolled environmental influences. So we've been building whole systems of monitoring what's going on in the environment, controlling for, and then feeding back onto the experiments through all these different parameters that exist in the lab and around it. Fine. So the first example is our, well, perhaps the closest to what we've been hearing, where we can tune the dimensionality of a simple weakly interacting but cold Bose gas, and these chips allow us to control the different confinement directions independently. So we can, for example, have a trap that can be more round, more three-dimensional, or more elongated, more one-dimensional, and we can toggle between them and continuously shift between them. Typically, you release atoms from a trap like this, and then you see phase fluctuations that manifest as density ripples in time of flight. This has been seen quite a long time ago, and one can quantify that in the one-dimensional regime. And here we sort of see time of flight sequences this way, and different degrees of compression and anisotropy in the traps, going from something that is very three-dimensional, so the gas expands as normal as a textbook BEC, towards something that has a lot of fringes. And now with the experiments that we've improved, we can do that more frequently. It takes less time to do one experiment. We can image the atoms better than we used to be able to do. So we can easily take hundreds of each of these images and do statistics and learn about this more quantitatively. So when we do that, we can go from a 1D regime to a 3D regime, as I said, and cover the whole crossover. So what you see here is a statistical average of the density ripples we see that's the blue line, and these are example images in the insets, and then that has been described over a decade ago theoretically how that looks like in 1D, and indeed the gases that we can make in terms of having a chemical potential temperature measured in units of the transverse excitation of the trap, they can be low chemical potential, low enough temperature to be fully described by those theories. But as soon as we start to become more three-dimensional, that goes away. Even if we do the appropriate corrections for interactions during the expansion, we get this red curve as a theoretical description by just extrapolating this 1D model. Doesn't work. The gas just becomes completely flat in the end when it's sufficiently three-dimensional in terms of its temperature and its chemical potential. So we get this. We can watch how this gas departs from a well-described 1D situation to the 3D case here, and then we can quantify that, and we can ask the question, what is it actually that drives this transition? Is it more the chemical potential? Is it more the temperature? What is sort of the parameter that matters? And what we find with these relatively extensive and systematic experiments is we can sort of, we don't cover the whole space of chemical potential and temperature, but we cover quite a lot of it. And what we see is when the chemical potential is sort of 4 h bar omega perp or so, nothing happens anymore. It's really three-dimensional. The blue color here means the density ripples are low. The red color means they're high, and in the opposite regime, we see that we indeed have the one-dimensional behavior. But what's interesting is in this in-between area where one can say, well, if the chemical potential is high, this is in this inset in this blue region here, it doesn't matter anymore what the temperature is. The gas is just coherent throughout its size. Whereas in a lower chemical potential region, about 2 or 3, actually temperature then matters. At low temperatures, we still have the we don't actually have these excitations as much, and then as we go up in temperature, we see more of that, and we sort of see more of the density ripples as would be expected for the one-dimensional case. Okay, so this is the second example. Then now we can, where it's sort of in between, we still have a BEC and a trap on a chip, which is too complex to go out and sell as a product, but it is something that we can use now as a tool to measure. So it's sort of the in-between case on my original graph, where we have still pretty complex setups where we integrate now samples that are independent of the laser cooling and the BEC making, and can measure something that is outside the cold atom domain. And we've been developing this method for quite a while. What is actually new in that, and with all these new techniques that we have with better imaging and higher repetition rates of the experiments, and more control on the chip assemblies, we can actually increase the sensitivity and also the spatial resolution to a point where this becomes a useful tool for an application example that I'll give you in a minute. So we can basically scan a BEC pretty quickly across the sample, and then by measuring the density that we get there, we can reconstruct the current density inside the A sample, and with this we can characterize the parameters we get there, small magnetic fields at relatively small spatial resolution, which is, in terms of magnetometry, it's a nice in-between case between highly resolving nanoscopic probes, surface probes such as NV center microscopes, and on the one hand, and on the other hand, the atomic vapor cell magnetometers that I will talk about afterwards in a minute. And sort of here you have a combination of spatial resolution and high sensitivity. So here's the application example that we're looking at. Next generation touchscreens will potentially look like this, where your phone doesn't break anymore when you drop it. It's flexible. Basically, any transparent material can be used, and then there's a spray out of a can with some nanowires in them. The solvent evaporates, and you're left with a random distribution of, in this case, silver nanowires of some tens of nanometers diameter and a few hundreds of microns length. And those networks, they make this transparent material conductive. But there's still issues in that the conductivity is very temperature dependent and has sort of random uncontrolled behavior. So one would like to have a probe to measure what happens inside these samples. We now have them in our experiment on the chips, and we can start to measure this. And we're quite confident that this is the right sort of parameter range to understand these phenomena. And of course, there's some interest in the physics of these percolating networks at a small scale. So now the third and last example that I want to talk about is really, now it's a bit of a stretch to really talk about a synthetic quantum system, because all we have here is a vapor of thermal atoms in a cell, and essentially the experiment is just to have a laser beam that pumps the atoms into one specific quantum state that's then magnetically sensitive, and then probe it with another beam to read out any external magnetic fields. It turns out that can be very sensitive. It also turns out that these two beams can be even combined to make a very simple device where it's just vapor, laser light goes through, we detect polarization or intensity or both, what comes out on the other side. At Princeton, they found about 20 years ago already that this can be as sensitive as the best magnetometers we had so far. Essentially goes into the attotesla per root hertz range of magnetic sensitivity. In the first paper, then they said, oh, and this is where the connection to my new work at PTB comes up. Oh, this can be used for measuring brain currents in humans, because those magnetic fields that we can detect here are small, but these sensors are so sensitive that they still pick them up outside the head. So that has been enough drive to miniaturize these things, and again with metrology institutes involved. NIST and PTB actually did some work together there before my time there, and this has led now to some commercialization, where now you can buy this piece of, looks like Lego, but cost unfortunately $10,000 a piece. But still, it's a good start. You lose some sensitivity, of course, it's not anywhere near there, but you now have a device that you can actually use, and people start to dream of all sorts of things now. The main one perhaps being a brain-computer interface, because now you can measure what happens in the brain without digging in, without touching anything, and you can connect it to a computer, and you can do all sorts of good and perhaps not so good things. You could have GPS independent navigation, because you can have magnetic field maps of anomalies in the earth, and you can You can, as you travel and you don't know where you are, you measure your local magnetic field map, and with a map matching exercise, you can position yourself, and then you can go into sort of biology and on a cell level do smaller scale measurements of processes that happen there with magnetic nanoparticles, for example, is also a direction that is being pursued in my department at PTB now. So here's the thing why this is important in what is called magnetoencephalography, where this is done. So unlike all the other medical imaging techniques, magnetoencephalography is a completely passive and non-invasive method. So you don't have X-rays, you don't have even external magnetic fields and RF excitation. As you have in MRI, you just simply listen to the brain's activity magnetically by placing sensors near it. It's something that's been sort of commercially viable since 20 years with superconducting sensors, SQUIDs, superconducting quantum interference devices. There's a research market for it, is about 200 machines around the world. The problem is that SQUIDs are cryogenic, and they're actually, because of that, quite far away from the head. So you don't get very good spatial resolution with that method because you're measuring too far from the sources of the brain. These new sensors, the ones that I've just shown, they can basically be directly on the scalp. So here's an example of the difference that makes. So we did an experiment where we just looked with a conventional SQUID system. Here's the signal. Here on the same scale is the same signal with these optical sensors. You can see is a factor of 3 to 5 greater, which makes a big difference. But the more important difference is that the proximity, especially in the cortical areas of the brain that are near the surface, you can actually distinguish between sources much better than you could before. So here's an example of that. So we did the simplest experiment you can do is what this thing does to me now. It's a visual stimulus. You shine a flash of light in someone's eye, and then here's a MRI tracing of a particular person. This is actually a real measurement through diffusion graphs. You can track the optical pathway from the visual nerve is here by the eye, goes to the center of the brain, and then it fans out in the visual cortex, which is here, the back of the head. And you can see, if you have two sensors nearby, you can actually distinguish different areas of this visual cortex. Whereas if you're far away as you were with the SQUIDs, you don't have a chance to see that. So we can actually see that this stimulus arrives as a signal in different locations on the visual cortex at different times, which is what we see here. And unlike all the physics experiments that we usually see, reproducibility here is a really big deal. It's really hard to actually, someone is in these machines, and you look at their currents and to see the same signal before and after lunch and with different people, even though you do the same experiment, isn't obvious at all. But here it works pretty robustly. We can see this peak, this time delay between these two signals is basically a manifestation of this visual stimulus arriving at different times. So now we can buy these sensors, but what we really want is something like this. We really want chips with a high spatial resolution and a full coverage of someone's head. One approach is to do this, just buy many of these sensors and stick them together. It works to a point, but then they crosstalk, they get too hot, and they're too expensive, and they're not robust enough and not reliable enough. So really, there's a need to do something like this, and hence we started that journey and built our own systems, which have sort of this type of scale. That's a few sensors in there, and here is our first detection of an actual brain signal with a sort of home built, I want to say, but of course they're built in a lab, and these sensors already have a high sensitivity, and what we're most proud of, have a higher bandwidth, so higher temporal resolution than the commercial ones, and so on that basis we'll build a bigger modular system, and ultimately the chips that correspond to the image I've shown. So this is sort of some further development of this. One can also measure at high offset fields, which is a big question as well. How much do you need to shield off external fields, and how much can you work with offset fields? You can lose some sensitivity, but then you can basically measure in the Earth's magnetic field environment and sort of the whole peripheral electronics and all that to be viable in a non-lab environment is something important to work on that. I don't want to go into details what we do there, but it is quite a big chunk of work that we're, I think, on a good way of. Yet I just want to flash another application that shows that you can really do very different things once you can measure small magnetic fields. So one thing in the medical sector is that to build a device that then becomes a clinical device requires many steps, also regulatory steps, and it's very difficult to convince industrial players to get into the business unless you have application use cases that are more immediate. So that was originally the reason why we got into some completely different area, which is this one, the batteries in electric vehicles, because of course electrification of transport is one of the big topics of our time in technology. And actually it turns out that the currents that flow inside a battery like this, the current densities, even when the battery isn't connected to anything, are measurable because with sensitive magnetometers, because they're so sensitive, and then even very small currents, relaxation currents and self-discharge currents are enough to measure things. And that's what we're here, for example, in this animation. I don't know how to start or stop it, but it's just running through. You see what happens when you charge a battery and disconnect it, and you wait in the first hour. There's a lot of change of magnetic field that you can pick up here with squid systems or with these arrays of these OPM optical sensors. And we can also measure with actually less sensitive flux gate sensors what happens in the charge and discharge process, and compared to electrochemical models. And these things fit quite well, and it's unusual in the field for the electrochemists to have spatially resolving techniques. So in terms of understanding the aging or monitoring the aging of batteries, it's an important tool to have. So there's an immediate and large industrial interest as well in this topic. So our first paper was immediately picked up by, for example, Mercedes-Benz, who published a similar paper on detecting defects with a method like this. So quite interesting, quite exciting for us. I just want to come to the end here and hopefully claim that I could convince you that the atomic gases are useful probes, not only for interesting phenomena in physics, but also well beyond in sort of real world application areas. And these people have contributed to all this work. The ones in boldface, in particular, to the experiments that I've shown here.
Thank you. Yes, and we have questions.
Thank you, Peter, for this very nice overview. I had a specific question about the finite offset fields that you are now able to work with. I mean, that used to be a major problem, that all these ultra high sensitivities in magnetometry with vapor cells were only working fine in zero fields. That's why you need these big shielding rooms, and you have to travel to Berlin to do this, and so on. Now you said you can work at finite offset fields up to a microtesla. What are the perspectives there, and how do you do it actually?
So there are multiple ways to think that way, but maybe I glossed over a bit that the sensitivity is quite a lot reduced in this sort of higher offset field.
How much
measurement.
at a microtesla?
So what we've demonstrated with this is picotesla. Okay. So you want an order of magnitude better than that to be able to detect the brain signals directly with that. Okay, it's not out of question. There are free induction decay measurements that you can do. The problem in the end, though, even if you find the right scheme to do this, is that if at the frequency you care about, say, the brain current, you have some environmental signal that is just much larger, then tell me what properties a sensor should have to distinguish the two. It's still hard, right, whatever sensor you have. So I think without the shielding, or at least without active compensation, it's going to be very difficult. But perhaps less shielding than the room that I wanted to show but didn't show, that has 8 layers of mu metal and is really a building from the outside and a small room from the inside because of that. Amazing to have, but difficult to sell practically.
Yeah. Okay, thank you.
Thank you. Okay, let's thank the speaker again and move on.